Hello, bonjour, hoi middag. Thanks for coming. Today we're going to talk about something new to many of you, I don't know. And it's Java on ARM. What's going up there? What's new? My name is Dmitry Chuyko. I work for a company named BellSoft, which you probably know because of binary distribution of OpenJDK we make. It's called JDK. It's CCK verified, and we provide support for that. And I'm on top enterprise contributors in OpenJDK space. But what's about ARM? We know ARM both as a company and processor architecture, which is a RISC architecture, very nice, for byte instructions. And it's been there for a long time. Of course, we know ARM processors that exist in many small or not so small devices, in our pockets, on wrists, in ears. And those devices nowadays are really powerful. So if you look at top mobile chipsets nowadays, they are as powerful as desktops, in fact. And even you can for example, buy a laptop which will be ARM-based. It's just a commodity product, and there are constant rumors about ARM-powered MacBooks. Right. And those processors typically have many cores. It's current reality. Even if you take, I don't know, some ear sets, well, earphones, you'll have two ARM cores inside. So here in this picture you can see 6 ARM cores and also 2 matrix multiplication modules in CPU unit. And those cores are different, 2 high power cores and 4 low power cores, which is typical for ARM chipsets. In modern cars, you may find up to 6,000 different sensors, a lot of data. And that data is processed by some microprocessors, microcontrollers, and sometimes the data goes to cloud. And if you imagine that, what typically happens is that some sensor, it may be like here, a temperature sensor is pictured, but it may be a camera, senses data to gateway, which again typically might be MIPS or ARM powered. And then gateway process data from different sensors and sends the data to a cloud. And then you can get something out of the cloud. Again, you can create some kiosk, for example, like ARM-based device with JavaFX or whatever you can imagine. Or you can even put GPU inside your gateway and do real-time video processing on relatively cheap device. Just check some of my other talks. And of course, industrial gateways are really widely available and well known. But what about different applications, like servers? Yeah, for a long time ago, there were some experiments to put ARM32 cores to combine a lot of that cores together and create a server. Well, there was a company called Calxeda that created such hardware. It was probably too early back at that time, but it was a good experience for the people who participated in that. And ARM cores are really different. So there are 2 currently used versions of ARM ISA, ARM7 and ARM8. And they exist in different kinds of devices that might be more microcontroller ones or something that is used for real applications. That are ones we are talking about, because we want to write applications in Java, for example, or in any other JVM language, and to run them on ARM processor. What's also interesting, we've already seen that same die can combine different cores together And Intel also creates now such a hardware, then low power cores and high power cores combined in the same chip. In a practical sense, when we work with ARM, we immediately recall some toy projects that we all love to do. Like yesterday, there was a nice talk about Escape the Matrix game, which is powered by Raspberry Pis. And you can assemble some toys or even industrial solutions using relatively cheap boards with ARM inside. But how Java runs on that boards? Of course, there is a port of OpenJDK, which is called ARM32-bit, just ARM32. It's open source since Java 9, or even 8. And yeah, of course, it works on Raspberry Pi. And since Java 9, you have all nice features of modules. And also, you can run JavaFX there on even really, well, low-end devices like Raspberry Pi 2. You can work with frame buffer and get very nice UI. So Java is like big or small. Sometimes it's considered too large. But in fact, there are options like minimal VM or client VM that can be as small as 4 megabyte, I mean minimal VM. And using minimal VM and runtime created with JLink, you can get 16 megabytes runtime at all. It's smaller than Go to run your, for example, command line applications. And it still has a lot of Java features. Of course, some features were sacrificed, but anyway. And then we talk about running applications on some ARM v8. I'd say we should keep in mind that, of course, it has different versions because of adding new cool features. Like, for example, support for cryptography, acceleration of cryptography, acceleration of checksum calculation, or processing vector mathematics. The vector extension is called SV, Scalable Vector Extension, and it allows to use vectors up to 2K length, which is very cool. And this year, it's not 2018, it's 2019, SV2 has been announced, which is also a next step in this ladder. Then we talk about ARM processors. You've already seen some ones, right? And what happens is that vendor gets a license from ARM, and it may or may not get some reference design, and then vendor creates its own processor, its own IP. And vendors are really different. You just can see some of them on this slide. In server space, ARM creates some reference designs with a clear intention to make good progress in speed, in power processors, and tech process decreases, and speed of processors grow, and the projected growth is very big. And they even say that current generation is not 30% faster than previous one, but like 50%, which is cool. Have you seen the previous generation? Anyway, new generation is better. But what are those processors? For example, Ampere Mag. Nice, cool processor. Single socket, up to 32 cores. And it addresses a lot of memory, and cores are very fast. Or Huawei, where you can imagine 4-socket machine, and each socket is 64 cores. And they also plan to add SMT support next generation. So a lot of cores, up to 1 terabyte of RAM. and KVM or Marvell ThunderX 2. There you can have 2 sockets, 32 core each, and each core is SMT4. That means 256 hardware threads in your server, and you can install 4 terabytes of DDR4 memory. And you have InfiniBand inside. It sounds powerful. Is it fantastic? Science fiction? No. You can buy this one, you can touch it, it's real, and it has standard form factor. It's that simple. Again, 256 hardware threads. You see, here we have less threads because, well, we need to fit the screen. And you can find those processors in real productions, in real hardware installations, in supercomputers. Like nuclear laboratories, for example, in US, in France, and UK. There's big clusters. And also, there's an interesting point here called PostK, which is a new Japan supercomputer produced by Fujitsu. They implemented their own custom ARM cores, diff SV support, and also diff interconnect for processors. And this is really powerful. This is their new major superprocessor, supercomputer. But what's running on that stuff? Different software. Sometimes it's not Java, it's just HPC, where you crunch numbers in parallel on a lot of machines. But sometimes you can just build a cluster and run your Hadoop or anything you like to. Of course, you will probably like to run Linux, and of course Java. And today, typically, we use something like Docker, right? And ARM and Docker, they made it easier for us because now you can cross-build ARM Docker images on your x86 machines, which is cool. So let's get back to OpenJDK. There are actually 2 ports that can run on the servers. First is the port we already mentioned. It's ARM32, which is, in fact, a unified port for ARM32 and 64-bit. But 64-bit part is being deprecated right now. And also, that port was developed by Oracle and then open sourced. And there's an alternative port, which is a current mainline. It's called AR64. It was developed by Red Hat. And we also participate in development on this port. It has old cool features of recent JDKs. And also, OpenJDK developers continue to evolve it in new projects that we all know, and you may hear about them here, like Project Panama or Valhalla with inline types. You currently can get Valhalla for ARM and run it. Things work. Thanks, BellSoft. And also projects like Graal, which is technically not an OpenJDK project, but still a key part of OpenJDK nowadays. And there are fixes, there is support for ARM 64-bit, and development and optimizations go on. So for us as Java developers, is there a difference where to run our Java programs? It's write once, run anywhere, right? Java is specification, so things should not break, right? Right. But they should not break if we write them correctly. So we can easily imagine an incorrect program that is not correct in a sense of respecting Java memory model. So Java memory model is the same. It must be the same on different devices, except we may have bugs. But hardware memory models are different on x86 and on ARM. So we may observe some interesting effects of different hardware memory model in our Java code. Then we just made a non-synchronized publication, for example, for a newly created object and a field which we modified after constructing that object. That's funny, right? But if you write program correctly, like you put synchronized or something, you're safe. And, of course, the goal of any port is to provide fast implementation. How we could make it fast? Well, basically, it's all about compilers. And as in any other compiler space, OpenJDK implies same techniques, peephole optimizations, and intrinsics. So intrinsics are small subroutines that serve as replacements for the code that you write in some language, like in Java. And those replacement is made by a compiler. Like in static compilers, they make such replacements for typical stuff, like for some libc calls or for something else. And in C2, of course, we also can use them, and they are widely used. So let's look at an example. Here is some Java function that does very important piece of math logic. Then we multiply two long numbers and get higher part of that multiplication. And it may be implemented using very smart math, just using proper algorithm. And then C2 does a good job. It generates quite optimal code. It's only 14 operations, each with latency 1, and some of them, they are pipelined. So the actual cost of this operation in JIT compiled code is less than 14 clocks. Except of some possible memory loads, but anyway, if the data is here, it's all cheap. But can we make it faster? Of course. Otherwise, why would I tell you about that? We can use special instruction. ARM is a nice instruction set, which contains, in particular, instruction that does exactly that. So why would we generate that many instructions instead of just one? Having, cost not 1 but 4, but it's a single instruction. And also, we might consider different alternatives, like let's write the same thing in C or C++. Will it be better? Unlikely, because we'll have the same code as C2 produces, and also a GNI overhead. Does it make sense to write some C2 IR sentence instead? Well, maybe, but again, multiple instructions, and then it may be rearranged by further optimizations. So let's try to use that single instruction, of course. It's basically very easy and not so easy at the same time. Because when we are trying to use new instruction, we have to define how it's encoded, how it's used, and to go to all proper places in Hotspot to make it, use it for our needs. So here, for this instruction, we had to define it in assembly, so like in macro assembler definitions to define its encoding. Also to make an implementation of the implementation for C2 to make it recognize a necessary pattern and to replace it by the piece of assembly that we actually need. And also it was detected as a new intrinsic in Hotspot, which we mark as Hotspot intrinsic candidate to make it easier for VM to process things. But we cannot do it blindly. We have to measure performance before and after and then compare. Of course, it's not so hard for this case. We just create a JMH micro benchmark, pretty dummy one, but it immediately shows us the improvement. And it's more or less like expected. So we have 4 clocks instead of 14, and we have relatively same speed up in the micro benchmark. Cool, right? Sounds easy. But what typical Java program does? Does it multiply numbers? It parses JSON, right? Or it generates JSON. That's a different task. So typical Java program operates with strings, or at least with some arrays that may be treated as strings in some corner cases. But strings nowadays, they are different since JDK 9. Of course, JDK 8 is the best JDK ever, but since JDK 9 we have compact strings. So string, any string, may be in fact represented in memory as later in one string or as a wide string. What else is interesting about strings is that you have a good program if your strings are less than 32 characters, of course if they are also later in one. And you also have a lot of strings around 8 symbols. That means you have a typical program and Hotspot does optimizations right for you. Otherwise, things become more interesting. So you have to know distribution for strings to get important cases for optimization. And then if we create string, all paths goes to a single important routine that has very simple name, has negatives. So we have to check whether the source array does it contain any non-Latin symbols. Well, it's easy to implement. We just write a loop and we check symbol by symbol, character by character. We check its value. If it's like negative, which means it's non-Latin, and if it is, okay, we create white string as a representation. But what do we do here? We load chunks of the initial array. And on ARM, we can load data in different ways. Like here, if we use general purpose registers, we have instructions that can load byte by byte, can load 2 bytes at once, 4 bytes, and even more. So which one is the best? Obviously the one that loads most data, right? Well, right and not right because of a single tiny problem. When you step on the memory you don't own, you have a problem. Because, well, you just get a segfault. So well-known technique is to make more narrow roads, more narrow reads, like reading 2 bytes instead of 4 and then byte by byte. But that's not optimal. Instead, we can do an intersecting pair loads and then filter the data that we have read twice. Okay, let's do it. There's a nice instruction in ARM instruction set called test, where we can use Bitmask to filter out the data. Did we solve all the problems? Oh no, we're just in the middle of the road. Because on x86 you have even 2 hardware prefetchers that help you, processor realizes that you load data sequentially, and loads the data ahead of time, prefetches it. But, we'll talk about that later. Let's talk about aligned memory access. You cannot just read from arbitrary address. Well, you can, but sometimes it may be expensive. Because it's better to read from some address which is divisible by 16, for example. Otherwise, you get penalty in your in performance of that read. And that penalty may be quite high. It's not covered by specification. It's the matter of your hardware vendor. And vendors are different. They implement hardware the way they like. So all you can do is benchmarking and trying to do your best. So in this case, we also can combine filtering data and wider reads to make preloop so that our next reads be aligned. Not that hard. But the overall plan looks really complex. And it turns out that implementing such logic will give us around 200 instructions, which is several cache lines on the processors we have now, which is not good, especially when we try to inline such code into other methods by C2. So it's better to have smaller code in most of cases. So for that cases, like we know, 32 is a magic number. We can run a simple loop, which takes just few instructions, and it has the same performance for that length of a string. And for larger data, we can make a call. And this is kind of special call. It's a jump in a thing that's called stub. The stub is a function that is generated during hotspot start. So it's a platform-specific code generated in one place, and then you jump there from your JIT-generated code. And that stub, all the complex logic exists, like alignment, overlapping reads, all the tricks. Okay, but that's not enough. As I mentioned, hardware prefetchers really help us, but sometimes you just don't have a hardware prefetcher. So some ARM hardware doesn't have it. And there's a solution which is called the software prefetching. You can issue a special instruction that says, okay, here's a hint for you, processor. I'm going to read that data in the near future. And you can do the same on Intel. There's also prefetching instructions. But by testing, by benchmarking, you have to determine what's the prefetching distance optimal for your hardware. What really helps your algorithms to prefetch good? Well, after some testing, adding prefetching and adding all other tricks allows us to get good speedups, especially for very long strings, which is a complex case, but the speedup is the most for long strings. And speedups we observe for different lengths, up to important length 31 or 32. There are no regressions, and sometimes they're really high. Then length is divisible by 8, obviously. Those were just two examples of optimizations we can make. And those optimizations, those and others, were delivered under the umbrella of JEP 315 by BellSoft and JVM. And they also include things like different operations for strings and arrays, and math operations that are really important. And you see, micro-benchmarking speedups are almost 80x, and that's for mostly like C2 code. You can also check latest Graal pull requests. A lot of work done by ARM in this space. Also a lot of micro-optimizations. So you will see similar numbers, like great speedups. Okay, micro benchmarks are good. We solved a lot of micro problems. What happens in large benchmarks? Well, let's imagine typical JVM benchmark that tries to measure performance of your enterprise application. And we may compare, for example, current under X2 machine, the Sam Xeon Gold machine, using about the same settings, a relatively small heap, and also those JVM settings are very minimal. So you see the performance is about the same, while our machine is slightly better. At the same time, it is about 2 times cheaper. Good deal, right? Don't trust me with those numbers. I know how to make them noticeably better for both machines, especially by using more memory. But anyway, for these settings, you see, they are really comparable. If you take another benchmark, which is kind of more micro benchmark, but large suite, you see the result is about the same. They are almost equal. Some benchmarks are better on ARM. Some benchmarks are noticeably worse because of missing vectorization for that hardware. But hardware with SV implemented already exists, like PostK, and several vendors have plans to implement SV, so that will solve that problem. But where do we actually get some ARM instance to run? Well, it's also easy. We just go to one of providers in the cloud and get that instance. Like we can go to Packet, which provides us bare metal instances from first generation of KVM machines, and newer one is C2 large ARM, which is Ampere. And you get, well, access to a bare metal machine, know some strange effects of virtualization, things like that, and it's really powerful. Or you can get a virtual instance if you're fine with it, which is way, way cheaper on the Scaleway. Different size of RAM and different SSD options. And there's one more provider which all of you probably are familiar with. It is AWS, which gives you a variety of ARM instances. From very small one, which is called A1 Medium, to really a bare metal one, the maximum configuration. And Amazon is interesting because they use their custom ARM chip design. They have their own design team. And the chip is called AWS Graviton. And it's really powerful. So just go and try one. Okay. So if you can see, vendor support is great. You can afford powerful hardware, and you can get it without having any physical setup. Just go to a public cloud and get an instance. You can use your favorite operating system, and vendors like Red Hat at ARM as their tier 2 platform, it is very good supported, and kernels are very stable, so things just work. You can run your favorite software, install your typical packages, libraries, no problem. And you can also install Java. Just please use newer one, it will be much better. And the easiest way is to get Liberica, and you can try Liberica JDK and Liberica Mission Control. If we have some time, we can try a small demo. Not sure. Or we can go to questions. Let's start with questions. Okay. Let's then try a different one. Okay. Let's go to some ARM server. Do I have Wi-Fi? No. Okay. I have Wi-Fi now. Okay, so I'm on Packet instance. You see? This one is KVM first generation. It has 96 processors. This one's third generation, so you better to work with second. But still, on this one, we can try Interesting. Just give me a sec. Something. Oh, okay. Let's go to a demo folder and check some script that I have here. All right. So this script starts 95 instances of Spring Boot Actuator application using AppCDS and also exposing some JMX ports to make this application work with Java Mission Control from remote machine. So we can try to run this one. Like here. So you see it starts. And it's a public IP. So I can go and check if it works. Not yet. All right, that's one of copies, and we can try some others. So they are started in separate Docker containers with 1 core resource per container, and also they eat up not so much memory, relatively tiny ones because of some tunings. Please check my other talks. It works pretty good. We can try to connect to them. Let's start Liberica mission control. I'll just move it to your... Okay. So you see, it tries to connect. I hope it will work. Oh yeah, it works. So with Liberica mission control release build from my machine, connecting to some cloud ARM instance somewhere, I don't know where, and basically getting all the information about the virtual machine that I run in Docker on that host. What's interesting here is that we can check some bins. We can start flight recording. We can check system information. You see operating system Arch is AR64. Available processors is 96. And all other information available to us. Things just work.